The Baeyer-Villiger reaction is a very useful conversion of ketones into esters using a peroxy acid. The original report of this reaction dates back to 1899, with many new applications and modifications being published since. The mechanism involves nucleophilic addition to the ketone, followed by an intramolecular rearrangement. The reaction is stereospecific, with the stereochemistry of the migrating group being retained, and regioselective, with the stronger electron-donating group migrating preferably. This evidence will support a concerted migration step as opposed to a stepwise process. Since peroxy acids contain a significant amount of the parent carboxylic acid, the pathway most likely begins with activation of the carbonyl by protonation. This is followed by nucleophilic addition of the peroxy acid to give a hemiacetal-like intermediate. The electron-withdrawing acetate group then allows for rearrangement, which results in loss of the weak OO bond. Rearrangement affords a resonance-stabilized oxonium ion, that is the conjugate acid of the ester product. Initial protonation of the ketone enhances the rate of the reaction by producing an electrophilic oxonium ion. The carbocation-like resonance structure reveals how electron-poor the carbonyl carbon has become. The electrophile then picks up the peroxy acid in a nucleophilic addition step to give a hemiacetal-like tetrahedral adduct. A proton transfer then activates the system by creating a good leaving group, and the rearrangement step has been set up. The system now has a chance to break the weak OO bond by undergoing concerted rearrangement with migration of carbon to oxygen. This provides a resonance-stabilized oxonium ion and a molecule of carboxylic acid, which is the reduced form of the peroxy acid starting material. The stability of the oxonium ion is described by the associated resonance structures. Finally, loss of a proton delivers the ester product, which in this case is an acycle and thereby called a lactone. Peroxy acids contain some of the parent carboxylic acid, so proton transfer to the ketone sets up an activated electrophile. This is then trapped by the peroxy acid, and proton transfer, followed by rearrangement, allows for loss of the weak OO bond. Loss of proton to solvent then gives the ester product. Let's examine how the experimental evidence leads to us invoking a concerted migration step. Firstly, when the alpha carbon is a chiral center, the reaction results in retention of configuration at that carbon. Secondly, the more substituted alpha carbon migrates faster, and the reaction is regioselective. Both of these observations agree with a concerted migration step. The electron-withdrawing acetyl group on the OO bond is pulling electrons towards itself. So it makes sense that the more electron-rich side of the substrate should migrate faster, and this accounts for the observed regioselectivity. The stereospecificity, where the configuration of the migrating group is retained, also backs up the concerted nature of this process. The alternative is a stepwise series of events in which a radical, carbocation, or carbanion is formed by the carbocycle opening up. Such events would result in a planar species in which the stereochemistry at the alpha carbon would be lost. Hence, a concerted migration step is most likely to be occurring. Additional examples of the Baeyer-Villiger reaction are shown here. In the first one, the reaction is regioselective since the stronger electron-donating alpha carbon has migrated. Since there isn't a chiral carbon in the starting ketone, there is no stereochemistry to be concerned with here. For the second example, the reaction is again observed to be regioselective, with the more electron-donating aromatic ring migrating faster. In the third example, the reaction is regioselective, with the more substituted alpha carbon more likely to migrate. It is also stereospecific, with the configuration of the migrating group being retained. The Baeyer-Villiger oxidation is a very mild and convenient method for converting ketones into esters through transfer of oxygen from a peroxy acid.